I'll begin with a word of prayer. Dear Father, we thank you for this day. Again, Lord, I thank you for the students. Just ask you to help us use this time wisely, Lord. In your name I pray. Amen. So I have just a few solutions to show you. Annoyingly, I fell asleep. Let's see here. And I still haven't found, like I have worked out solutions to 152 and 153, but I cannot find them. So I'll have to work them again, which is not a big deal, but it's something I gotta do. So problem 145, what's the least squares method? If you're fitting, I mean, it depends on what your model is, right? But if your model is a line, then, first order of business is to define parameters that describe the model, in this case, C1 and C2. You could just as well make this SpongeBob and Pac-Man. It wouldn't matter. I mean, these are just, variables that we're going to figure out what they are. So plugging in the data, we get this system of 5 equations and 2 unknowns, which is, of course, overdetermined and inconsistent, which technically speaking doesn't have a solution, but we know that we can solve the normal equations to find the best fit approximation. We discussed how that gives us the closest thing to a solution that's not technically a solution. So this is called least squares, the least squares method. So I take this matrix, multiply by the transpose, that gives me this. It's 2 by 2, so I can find the inverse, right? So there's my inverse. Then I multiply the inverse on the normal equations, and I got that. Did you guys get this? Okay, good. Because I worked this out before class, and odds of me making an arithmetic mistake in this kind of question at this point in my life are pretty high. So it comforts me to know that you also got this. Yay! So that's one of the problems I have solved. The other is this one, problem 150, 151. So we proved that symmetric implies normal in class. A 2 by 2 normal matrix, which is not symmetric. I think we actually talked about that kind of, sort of, yesterday, right? In fact, there's your example again, Bethany. So, let's see here. So normal, of course, in the real case is just R times R transpose equals to R transpose times R. That equation's true for an orthogonal matrix because both of those are the identity. Of course, this is also met for symmetric, anti-symmetric matrices, right? In the context of a complex matrix, you need that the conjugate transpose times the matrix is equal to the matrix times its conjugate transpose, right? So in the complex case, it's a little more complicated. Pun not intended. So this one, I don't know, I hope you found this homework problem for me was actually kind of, it looked scary when I looked at it to start with, and then when I actually got into it and tried to work it out, I was like, oh, this is actually kind of fun. Maybe you had that feeling too, I don't know. Yep.
How do you find the norm of a matrix? Because I thought there was a formula like somewhere on one of the past solutions that had to do with the trace.
Yes, but this is, right, but this would not be the norm of a matrix. This is the norm of the vector AX.
Oh. Okay.
If I said otherwise in the problem statement, shame on me. But yeah, the norm of the matrix is the trace of A transpose square rooted, which is a sneaky formula for the square root of A11 squared plus A12 squared plus A13 squared plus plus ANN squared. Or if it's a complex matrix, it's a tricky formula for the square root of the modulus of the first component squared plus the modulus of the second component squared plus the modulus of the last component squared square rooted. But yeah, in that case, it would be the trace of A times A conjugate transpose, right? Well, what was the formula? The inner product of complex matrix Z and W was the trace of W. How'd it go? I think it was the trace of W conjugate times Z transpose or something like that. Anyway, it's the sum over I and J of Zij times Wij conjugate. So anyway. So any questions? I mean, I don't know. Then if A is normal, then A minus Ci is normal. Well, that actually is just straight matrix algebra and properties of the transpose, right? E is a little bit tricky, I suppose. So if lambda is an eigenvalue with normal matrix A, then lambda is also an eigenvalue of the transpose. So if a lambda is an eigenvalue of A, that means the null space of this is non-zero, which means that there exists an X such that that. But since A is normal, that means A minus lambda I is also normal by part D, which means that also we have that the norm of that is equal to the norm of that, right, by A part C, which then means that this is equal to that is equal to 0, which is to say the only way we can have a vector, sorry, what's wrong with me? I'm just going to start talking about windshield vipers if I'm not careful. Sorry, I used to have an Indian friend I would always make fun of because he couldn't say windshield vipers. If I wanted to aggravate him, I'd be like, Tapomoy, say windshield vipers. He'd be like, shut up. Shut up. I miss Tapomoy. Anyway, that being 0 forces this vector to be 0, which is to say that X is in fact a element of the null space of A transpose minus lambda I. And it's non-zero, which is to say that it's an eigenvector for A transpose with eigenvalue lambda, right? Now, this is pretty special. Now, you can prove for an arbitrary matrix, not a normal matrix, just any old matrix, that if lambda is an eigenvalue for A, then lambda is also an eigenvalue for A transpose. Because you can just take the transpose of the characteristic equation and it's still the same characteristic equation for A and it's A. Like how you define the characteristic equation is what? Determinant of A minus lambda I, right? So if you think about it, what's the determinant of A transpose minus lambda I? Well, it's the same polynomial because the determinant of the matrix is the determinant of the transpose, and I is equal to I transpose. So a matrix and its transpose always share the same eigenvalues, right? But that's not to say that those eigenvalues have the same eigenvectors. All right, that's a stronger thing to say. And that's what we're saying in part E, is not only is X an eigenvector for A, it's also an eigenvector for A transpose, and with the same eigenvalue. There are other things you can relate, like a matrix and other things, like a matrix and its square. Those have the same eigenvectors, if you think about it. They don't have the same eigenvalues, though, right? If X is an eigenvector for A with eigenvalue lambda, then X is an eigenvector for A squared with eigenvalue lambda squared. You know, so there are relations between like a matrix and its powers and the eigenvectors. But anyway, let me get back on track here. So there's that one. Excuse me. And then part F here. In a normal matrix, the corresponding eigenvectors are orthogonal. So what did I do? I think I suggested a slightly different argument to some of you guys when we talked about it the other day, but this is probably also right. I mean, I hope. So you have x and y eigenvectors with lambda 1 and lambda 2 distinct. Look at the inner product of x and y. We want to show that's 0. So what I do was to look at A transpose AX is equal to, now, this is equal to that? Okay, so like generically speaking, guys, there's a general identity in the complex case, right? In the complex case, if we have t, or just generically speaking, if we have t of x, y, you know that gives you x t adjoint y, right? So this is generally. So this could be a complex inner product or a real inner product, all right? In the case f equals to r and dot product, right? If you have ax dotted with y, it's pretty easy to prove that that's a dotted, good grief, it's sad, x dotted with A transpose y. So, in other words, in the real case, the transpose is the adjoint. All right. And so, like this is again a general identity. This does not. I'm not assuming anything about A here, except that it's an n by n matrix. All right. We could prove this. I will once we're done with this problem. I'm going to leave it here. Remind myself to do it. But since A is normal, that means that, so what I should have here as a general identity is just the transpose of that, right? But the transpose of this is what? I think it's that again, isn't it? This matrix is symmetric, is it not? So that's that. But let's see here. On the one hand, we have the lambda 1 from the x. Over here, we got the lambda 2 from the y. But then the cool thing is, guess what? Still eigenvector with eigenvalue 1 for x, and still eigenvector with eigenvalue 2 for y. Right? So we get that minus that times that is 0. But since lambda 1 minus lambda 2 is not equal to 0, let's see here. Well, since these are distinct, it implies that that's different from 0, which then implies that this must be 0. Now, the solution I was guiding you towards was something different the other day because I was not fully appreciating all of the data you have from A, B, C, and D, right? So you might have found a different solution for part F. Yeah?
Isn't it possible that you could have
Uh-oh.
them distinct, but that would be 0, like if lambda 1 was negative 1 and lambda 2 was 1, because they're squaring both of them?
Ah, that does seem possible, doesn't it? There is a hole in this solution. 'Cause I was just thinking that, because that'd be like lambda 1 plus lambda 2 times lambda 1 minus lambda 2. And you point out that even though lambda 1 minus lambda 2 is non-zero by assumption of distinctness, lambda 1 plus lambda 2 could be 0, right? Let's see here. I guess in my argument, I might have to treat that as a separate case, huh? If lambda 1 plus lambda 2 was equal to 0, that would mean that lambda 1 is equal to minus lambda 2. Let's see here. Yeah, my current solution has a gap in it, for sure, yeah. Agreed. So I think the thing I was guiding you guys towards might be better, I don't know. Do you feel like you had an ironclad solution for F?
No, because we had to assume that A equaled A transpose.
You had to assume that A equals A transpose. That is definitely not the case. Wait a minute. Is A symmetric?
Well, A might not be, but A times A transpose was.
Yeah. Yeah, but... Huh. No, I don't think we're supposed to assume that A is symmetric in part F. All right, so I'll have to think about that, see if I can fix this. I'm working on the solution today, so I'll work on that. Oh, let me just address this right quick. How would you prove? So this is what? This is a matrix formula for that is what? AX transpose times Y, right? This is a 1 by n times n by 1. It's a 1 by 1, right? So this is the right formula for the dot product as a row times column multiplication, right? And so by sock shoes, that's X transpose A transpose Y, which is thus X dotted with A transpose Y. Yep. There you go. So I wanted to make sure what I wrote in purple is not a mystery to you. That's something you ought to be able to derive without breaking a sweat, right? Well, that might not be true today. Anyway, it's going to be horrible today. So it's 90 for Lanvo. Just saying. Any questions about 161 or 162? Actually, did you actually work 161 or 162? So the neat thing here is, given any linear transformation from V and W, we can define a corresponding map from the W dual to V dual by that rule. All right? And that rule right there doesn't depend on choice of basis or anything, right? This is just like a coordinate-free, nice, relatively simple, what else could you write down kind of formula. So what we're saying is that S acting on something from W dual gives me something in V dual. Well, something in V dual is a mapping from V to the field, right? So to define S of alpha, which would be in V dual, I have to say what it does to a vector in V, all right? So I define that to be alpha of T of V. This makes sense because T of V is a W vector, and alpha takes W vectors and gives us back scalars from the field. So this for all v and v defines S of alpha as a W dual vector. And this construction is called the, I think it's called the, well, is it the adjoint? Or is it, I don't, the terminology varies. Sometimes it's called the adjoint. I might call it the transpose. The reason for that is fairly obvious as you go on here. So there's a proof that it's linear, yay. And then the matrix of S with respect to the dual bases would be that. And let's see here. So if I look at the, let's see here. So if I let S act on the jth dual basis of W, right? That should give me a dual vector in V. This is in W dual. And so if it's in V dual, that means I can build it from the dual basis for V. The way to do that, to get components, I'd let the transformation act on the basis for V. That gives me components with respect to the dual basis. There's my dual basis for V. So that's an expression to expand S. This expression tells me that the ith component of this is that guy. It's S of GJFI. And so this then tells me that the ijth component of this matrix, right? So this would tell me about the jth column and the ith row. So the ith row and the jth column of this is equal to exactly what we have up here, right? But this, by definition, is GJ acting on that, which then, by the similar discussion for T, is the jith component of the matrix for T, which is to say that the matrix for this S is the transpose of the corresponding matrix for T. So that's the kind of neat thing, is that this construction gives you a new transformation on dual spaces where the matrix for the original transformation is transformed to the transpose. That's why this construction is sometimes called the transpose of a map. So the transpose of a map goes from the dual space of the codomain back to the dual space of the domain. With that in mind, problem 162 is not surprising. By the way, here is sample calculation, and here is a more gory, ugly version of the calculation I just talked us through. So like here's it in gory detail. The matrix of this would be this, which would be that, which would be that, which would be that, which would be that. So if that kind of presentation of the calculation is better for you, look at that. And here I'm deriving some things we've worked out already this semester. For example, that if the coordinate vector of this with respect to the dual basis is that, then you can calculate that the C1, for example, is this thing acting on F1, right? So I'm deriving the relation between the dual basis components and the action on the basis. We've already walked down this path before, but you might have forgotten. Anyway, going on, 162. So the two pages I just kind of glossed over, we've gone over those before. In fact, even, let's see, we had dual bases on test 2, right? Yeah, so I've actually talked about that before test 2, what I just went over. Okay, so here, again, we're using the transpose of the map to T, and the claim is that if T is surjective, then S is what? Injective. If T is injective, S is surjective. And if T is a bijection, S is a bijection. I think, if I remember right, the problem is that. So the argument's relatively simple. I mean, basically, we just use the previous problem. So we have T is surjective. That means its matrix is what? Rank M, right? If T is surjective, that means it hits everything in W, which is to say that its matrix has no row of zeros, right? Which is to say that it's full rank. And anyway, so the column space of A has to have, the column space of the matrix for the transformation has to have dimension m, which is the dimension of W, and that suggests that there are m linearly independent columns of that, which means that the transpose has m linearly independent rows, which is to say that the matrix for the transpose is an n by m matrix with m linearly independent rows. What's that say? That says it has no row of zeros, I think. I could be wrong. No, that says it has m, how to say this? It has m linearly independent. Oh, I can't, m and n, I'm all mixed up. But anyway, if you work through it, you can argue that the null space of the transpose is 0 from this. Like I said, each column, and this is a pivot column, so the null space would be 0. Which then would say that the kernel of the transpose map is 0, which would say that S is injective. All right. And the argument's pretty similar for part B. You can use the fact that if the matrix for T is, if T is an injected, is one-to-one, that tells you something about the number of linearly independent columns. I'm sorry. This one was S is injective. So that tells me that the kernel of the transpose of the matrix is 0, which tells me something about the number of linearly independent rows, which then tells you I have that many linearly independent columns in the matrix for T, which is to say that that's surjective. Yeah. So anyway, I don't think I'm doing justice to these arguments at the moment talking through them, but the larger point is because the matrix of S and T are related by transposition, anything you know about the number of linearly independent rows or columns for one tells you something about the number of rows or linearly independent columns for the other, which then tells you about the injectivity or the surjectivity of the maps involved. And then part C follows from parts A and B put together. Yeah. All right, well, I'm going to put this away. I just wanted to leave the rest of the time for questions for you guys. That's all I have for the moment. Do you have any, if there's a particular one that you were particularly vexed by, you'd like to see me work through. It's not suffering. I like these things, actually. But is there a particular one that was troubling to you that I can work through here? If you'd like, I could try to run through the very verbose partial differentiation one. Should I try that? What you guys? No preference? All right, well, let me take a swing at it. No, because I said there was no matrix exponential on the test, and that's what the application of the matrix exponential was, differential equations. So the the differential equations went the way of the matrix exponential. Yeah. Okay. Nothing important. Let's see here. So can you guys read the formula for me? All right, good. So let us write down the partial derivative with respect to f of x. With respect to x, we got what? Actually, let me get to the point. The gradient of f is partial f partial x, partial f partial y, right? And so this is 0 at a critical point. Like, critical points are where the gradient's 0. If there are any such points. And so you're telling me this was 10x. There's my fx, right? The other notation for this, guys, would be just f sub x and f sub y if you prefer that notation. Let's see here. Partial derivative with respect to y gives me 8x plus 10y minus 8. So a critical point would be where both of those are 0. Are there any solutions to that? So we've got 10x plus 8y equals to 10. And we've got 8x plus 10y equals to 8. In other words, we've got 10, 8, 8, 10, xy, 10, 8. So let's see here. What's the inverse of that matrix? (100 minus 64). Flip the 10 and the 10, put minuses on the 8. You're like, I could have solved this faster by substitution. Yeah, I know. Fine, you got me. All right. 36? 0? Okay, so yay, one critical point. What's the critical point? 1, 0. So we only have to, can this be the whole test? Says people who've already had calculus 3. All right, see. Yes. Okay, so let's see here. Now, I told you guys that the theorem is that f of xy, right, is f of 1, 0 plus, well, the gradient of f at the point 1, 0 dotted with x minus 1, y minus 0 plus, well, we could say, well, anyway, over here we have x minus 1, 0 times the Hessian matrix times x minus 1, 0, right? This is the you know, multivariate Taylor's theorem. But the thing is, for a critical point, of course, this is 0, right? So since that's 0, this is the dominant near 1, 0, right? So what is f of 1, 0? I think it's 0. Because if y is 0, 0, 0, 0. So I get 5 minus 10 plus 5. So f of, yeah.
Can you just explain why it's 0 there and y minus 0 on the term before it?
Oh, well, one is right and one is wrong. Which one's wrong? The one that's just 0. You're right. I had a choice to make, and I chose poorly. I should have kept the y. Yeah, thank you. Sorry about that. Now, this is just 0. So my point, guys, is that this quadratic piece over here is the dominant, you know. So this is fxx, fxy, fxy, fyy. That is the matrix of partial derivatives there. So we can figure out what that is. What is that, if I call that thing the matrix of Q? Ten, 8, 8, and, oh, weird. Oh, wait a minute, no, that's weird. Okay, phew. Wait a minute, no. Now weird. Man, that is a coincidence, okay? That is not what's generally going to happen. Like this and that being this, that's weird. That's just... Anyway, the larger point here then I'm more interested for you guys is to understand, okay, so that's a quadratic form, right? It's a quadratic form with inputs x minus y and y, right? I mean, you could write this as a quadratic form and x minus 1 and y. Yeah? So anyway, in fact, I think it's probably healthier to, instead of thinking about x's and y's, for us to think about, say, h and k, all right? And basically, our goal is to find h bar and k bar, which simplify formula for Q. Yeah. And so this is a symmetric matrix. We can find the eigenvalues. And so in so doing, and I don't think I actually said for you to do all this, right? What did I say? If I was to read my own problem statement more carefully, I think what I've told you is just to write down the Hessian, which we just did, and to analyze, looking at the eigenvalues of this, whether it's what? A max, a min, or a saddle. So I don't think I actually said to find the formulas. I'm getting too far into it. Yes. So we don't actually have to find the h bar, k bar formulas for this. And so what I'm trying to say is if I was to ask you to find the formulas for h bar and k bar, quote unquote, I would do it in the context of a less cluttered problem like I had earlier in this assignment, like problem, I like, for example, problem 146 or 147, that's the kind of thing that if I was going to ask you to find explicit formulas for the barred coordinates, I try to do it there. Because here you're wrestling with something else, which is x minus 1 versus h and y versus k, and how do you make that transition? It's the same question of how do you define like the limit, the derivative in terms of a limit. Do you use x minus a in the denominator? Do you use h in the denominator, right? And so that's a confusion that's worth confronting, but it's not a linear algebra confusion. It's a calculus confusion. So I'm trying to I would stay away from that for the test because I think it's complicated because of the problem of interpretation. All right, anyway, but that said, we can rescue this problem. The problem's still interesting because we still need to find out what are the eigenvalues of this, right? So how do you figure out the eigenvalues of that? Because that's what we needed to do to answer the question, right? So that's lambda minus 10 quantity squared minus 64 difference of perfect squares. So that's lambda minus 10 plus 8 times lambda minus 10 minus 8, which is lambda minus 2 times lambda minus 18. So apparently, the eigenvalues here are 2 and 18. Consequently, f of 1, 0 is a local what? Minimum, yay. All right. I think we should probably go back and work like the first or second problem. Which one do you guys want to see me do? Yeah, we can do that too. Let me do that next though. So again, would you guys rather me work 146 or 147? 147. All right. But yes, next up, the adjoint. Just trying to keep with the current arc of the story here. By the way, you could have also found you can find the quadratic piece by just making an explicit, you can replace x with x minus 1 plus 1 and leave y as y. If you make that algebra substitution in the original formula, you'll find the Hessian by just algebra. But anyway. there is a way of, for a simple enough function, seeing it through direct algebraic manipulation. I digress. So 147, did I hear? Oh, you guys make me working. You guys making me work. Problem 147. But that's probably for the best. Q of x, y, z. And we've got 5x squared plus 5y squared plus 2z squared plus 8xy plus 4xz plus 4yz. All right, so Q of V is V transpose AV, where A equals 2. So we got ourselves a 5, 4, 2, 2, 5, 2, and symmetric. All right. So there's the matrix. Now we need to calculate the characteristic equation of the 3 by 3, which of course is the most computationally intense thing you might face on this test, right? All right. Let's see here. Oh, okay. Sorry, thinking of tricks, but nothing pops out at me. 5 minus lambda times 5 minus lambda times 2 minus lambda minus 4 minus 4 times 4 times 2 minus lambda minus 4 plus 2 times 8 minus 2 times 5 minus lambda. All right. Which is 5 minus lambda times lambda squared minus 7 lambda plus 6 plus 2, plus 4, or, screws. All right, let me just multiply that stupid thing out. That's going to give me, famous last words here. All right, so this, before I multiply that out, what's that simplify to? That simplifies to 8 minus 4, which is 4 minus 4 lambda. So this whole thing gives me minus 16 plus 16 lambda. By the way, guys, you always want to look for factoring by grouping before you do this kind of multiplying out. But I don't know if I see anything really popping out at me. Maybe I should think harder about that before I go further. Let me at least look for factoring by grouping before I foolishly abandon it and multiply everything out here, right? So what's in parentheses here simplifies to what? Oh, thank you. It's less impressive if you know I was aiming for that trash can. I shouldn't tell you that. Oh well. So this is what we have there, right? So, why did I erase that? Idiot. Right, so 6. So this factors, right? That's lambda minus 1 times lambda minus 6. That's kind of nice. This business here is 16 times what? 1 minus lambda, right? Or lambda minus 1. Can we trade that minus for a plus? Yeah. I am starting to think that there might be a lambda minus 1 to factor out here. Let's see. And then over here, what you got? You got 2 lambda. Oh yeah, I'm feeling good about this. So plus 4 times lambda minus 1. Yay! Now, if I had foolishly just multiplied everything out without thinking, like I was starting to do, I would have lost the opportunity to factor by grouping the lambda minus 1, right? Just, it's there everywhere, so I can factor it out. Now, what if I had done that? If I had just multiplied everything out and made it into some big gory cubic, what could I have done then? I could have still had the common sense to go, you know what? This is a problem that has been made up by a person who's not interested in working with ugly decimals. So in my heart, I know the answers must be integers. What's the simplest integer that you could make an answer? 1. So you would then plug 1 into the cubic, and after you plugged 1 into the cubic, you'd find out it was 0. At which point you would realize you could use long division to factor out the lambda minus 1. Or you could use factoring by grouping. Anyway, you should be looking for things to be nice if you can. But on the other hand, there is computation, right? So anyway, there's lambda minus 1. And so we got 5 minus lambda times lambda minus 6 plus 16 plus 4, if I haven't made a mistake. All right, so that gives me lambda minus 1 times what? You got minus lambda squared. How many lambdas do we got? Plus 6, plus 5, plus 11 lambdas, minus 30, plus 20. Continued over here. The characteristic equation, determinant of a minus lambda I, equals to lambda minus 1 times, let's factor out a minus 1. Then we've got lambda squared minus 11 lambda plus 10, yeah? Well, you know, it factors again. All right, so that's lambda minus 1 with a minus out front, and that's lambda minus 10 times lambda minus 1. Yay. So we got lambda minus 1 quantity squared times lambda minus 10. Is this what you guys got? You monsters.
Yeah, I was doing that same thing, and then I read the rest of the problem, and I was like, oh, he gives it to us.
All right, fine. I'll keep moving. That's good. The likelihood of there being a 3 by 3 characteristic equation on the test just increased dramatically. Let's see here. Sorry. All right, so this has, of course, algebraic multiplicity what? This has algebraic multiplicity. All right. Yay. I like that you're saying that with confidence now. That gives me some hope. Let's see here. So a minus I is what? You got yourself a 4, a 4, a 2, a 4, a 4, a 2, a 2, a 2, a 0. Not a 0, a what? A 1. Aha, so it's fairly clear that this is row equivalent to 1, 1 half, but let's keep 2, 2, 1 because it's just nicer. Right? So there's really only one equation here. If we let UVW be an element of the null space of A minus I, what's that tell us? That tells us that 2U plus 2V plus W equal to 0. So I'll solve that for W, minus 2U minus 2V. In other words, we get that UVW is equal to U times 1, 0, minus 2, plus v times 0, 1, minus 2. Yeah? So, of course, the eigenspace with eigenvalue 1, we can write as the span of 1, 0, minus 2, and 0, 1, minus 2. But this is not the kind of, these are not the kind of vectors that are going to give us the nice eigenformulas, because that's built on an orthonormal basis, which we know exists for the symmetric matrix by the spectral theorem, right? So that there exists an orthonormal eigenbasis does not mean that every eigenbasis is orthonormal. Here's an eigenbasis for the eigenspace 1, which is neither orthogonal nor normal. How do you make it orthonormal? You have to run GSA on this set, right? Let me call this thing U1. Let's call this thing U2. Yes, we do. I'm just doing this one. But, I mean, yes, we also need the third eigenvector. Do you want me to just do that now? Okay. Like, I know that the third, by the spectral theorem, I know that the third eigenvector will be orthogonal to both of these. In fact, anything in the span of these is orthogonal, because the spectral theorem says, among other things, that E1 perp is E2. Because there's just the eigenspace 1 and eigenspace 2. The direct sum is the whole thing, and they're orthogonal complements. So I won't get into trouble by doing this now. Anyway, the point is, what's the length of U1? It's 1 over square root of 5, 1, 0, minus 2. Yeah? And then U2 prime is what? It's U2 minus U1 prime prime dot U1 dot U2, U1 prime prime, which is what? 0, 1, minus 2, minus, what do we got? We got 1/5 from the normalization factor squared. The U1 prime prime, this dot that, gives me 4. And then, of course, the 1, 0, minus 2. What's this give us? This gives us, let me put a 5th out front and do this calculation with a 5th factored out. So we've got 0, 5, minus 10, minus 4, 0, minus 8. I gotta be careful about the signs here. Just sort through that for just a second. Yeah, okay. And so 1/5 of what we got? Minus 4, 5, minus 2, yeah? So that tells me that my U2 prime prime is 1 over the square root of, 16 plus 25 plus 4. Is that anything nice? Not particularly. Square root of 45, I guess. I mean, we could simplify that further, but I'll leave it like... Oh, I'm an idiot. If I could just hold the thought in my brain for 2 seconds. So the normalized U2 is 1 over that times U2 prime, which is 1 over the square root of 45 minus 4, 5, 2. Minus 2, rather. All right, so, and then, of course, yes, we have to, so in other words, the eigenspace with lambda equals to 1 is the span of 1 over root 5, 1, 0, minus 2, and 1 over the square root of 45, minus 4, 5, minus 2. Are those, is this now an orthonormal basis for the lambda 1's eigenspace? Yeah, I think we're good. Because when you take the dot product, we get 0, they're normalized, yeah.
I just for the U2 time where you don't figure out for the dot product, it obviously doesn't matter like whether you do U1 or U2 first.
Yeah.
But in general, like for the projection,
It does matter in the complex case. In the complex case, it matters because we'll talk about that more when we talk about T star in a second here.
okay, so like if you were doing it with matrices or something,
If they're real, it doesn't matter.
okay.
The real inner product is symmetric, but the complex is conjugate symmetric. So there's a distinction between A inner product B and B inner product A. They're complex conjugates of one another if we're talking about a complex case.
Okay. So then which one would you put first? U1 or U2?
I don't remember right offhand. Yeah. I have to work it out. Yeah. Okay, so the eigen2 space, let's finish this thing, would be the null space of what? Net lambda equals 2, lambda equals to 10, wasn't it? A minus 10i? 10 was the other eigenvalue, wasn't it? Yeah. Okay, so that would be the null space of what is it? Is it minus 5, 4, 2? And then what? Again, a minus 5. What's over here? 2. Down here? Minus 8, yeah. Now that actually would require me a few row operations to actually sort through, right? It's not obvious like the other one. Let's see here. So I would say A minus 10i is row equivalent. I'd put the 2, 2, 8 upstairs because I like that. And I'll leave the 4. I'm going to multiply that first row by 2. And then, so this is 2, 2, 8. I'm going to subtract 2 copies of that. 0. I'm going to 0 those out. Subtracted 2 copies of row 1 from row 2. So that gives me minus 9. 18. Let's see here. And I have to subtract 5. I have to add 5 copies of row 1 to row 3. Adding 5 copies of row 1 to row 3 gives me 0, of course. It gives me 20. 12 plus 10, rather 10 plus 8 is 18. Let's see here, 5 times minus 8 is minus 40. Minus 40 plus 4 is minus 36. I like you. So this, of course, is equivalent to because these are, you can just, those are equivalent. I mean, there's the same row multiplied, right? Twice, minus 2 times row 2 is row 3, so we can get rid of row 3. And then, let's see here, 2, 0, 4, 0, 1, 2. I think that's it. Yes, this one, yeah. Which probably indicates that here too, right? Yeah. So when I subtract 2 from there, maybe I should just leave it as minus 2. I'm going to put that as minus 2 and, oh, I'm an idiot. Sorry. So minus 1, I'll leave it minus 1, 2, there, divided by 9. So if I add 2 copies of that one to that one, I get 0. 12, right? If I haven't made a mistake. Anyway, we'll find out soon. So if you have that UVW is an element of, the eigenspace with lambda 2, then that means that 2u is equal to minus 12w, and it means that v is equal to 2w. So we can set, I'm going to set w equals to 1. that gives me the vector what does it give me? Okay, so this u equals to minus 6v, right? 6w rather. So I got minus 6, I got 2, I got 1, and I better normalize that thing. Square root of what? 36, 41, yeah. And you can check that this vector is perpendicular to both of these guys if we did things right. Es no bueno. I do not get that that's perpendicular to that. Uh-oh. So I made a mistake in my calculations. Anybody remember what you got for the eigenspace of 10? No one remembers? All right. Tell me the matrix. What's the matrix? What's it? The original matrix. Wait, 5, 4, 5, 2, 4. Uh-huh. Eigenvalue is 1, 1, 10. And the eigenvector of eigenvalue 10 was 2, 2, 1. We should have gotten 2, 2, 1. So I did something wrong in these calculations somewhere. It doesn't really matter. The point is, I mean, it matters. Two, 2, 1, I said, right? I mean, you can try that out here. 2, 2, 1, right? 4 plus 4 minus 8, 0. 8 minus 10 plus 2, 0. Minus 20 plus 16 plus 4, 0. So you can easily check that 2, 2, 1 is in the kernel, meaning the null space of this matrix, which is what we want. But of course, this should have gotten it for us. I've made a wrong row operation somewhere. You know, that's my, it's my own stupid fault for not showing all the details, but I was trying to save us some time, and oh well. Now, of course, we still have to normalize square root of 9. And so in total, we get eigenbasis, what? In summary, we can form our eigenbasis beta 1 over the square root of 5, 1, 0, minus 2, 1 over the square root of 45, minus 4, 5, minus 2, 1 over 3, 2, 2, 1. Right? And you can check that this is perpendicular to that, and this is perpendicular to that. I'm scared to check. Yeah, it is. Okay. So there's an orthonormal eigenbasis for A, right? And if you were to calculate beta transpose A beta, what would you get? You would get 1, 1, 10, like that. And you can make this, you can define x bar, y bar, z bar. How would you define these? These would be equal to the basis matrix, right? Transpose times x, y, z. That would give me the formulas, right? Or we could also write x, y, z equals beta times x bar, y bar, z bar. This would give you formulas that you could then plug into our original expression, and after you multiplied it out, what would you be left with? If you actually took these formulas, right, and you plugged them in to that, what would you be left with? Right. So you said x bar squared plus y bar squared plus 10 z bar squared. Exactly. That's what the theory we've worked out proves.
Can you get half a problem too?
And I get half of problem.